Hello everyone, I hope you are doing well. So in today's video, I'm actually going to go through the 2019 Maths Methods Exam 2 extended response questions. I've had a couple of my students begging me to finish this exam. So yeah, that's what I'm going to go do today. And guys, if you want private tutoring, please, you can always visit my email down below and email me and we can have a discussion. I tutor physics, specialist methods and chemistry. So yeah, let's get down with this video. Alright, question 1. F of x is given by this and we know the domain's all real. Find f dash of x. So I'm going to first define this function. So f of x is defined from x squared times e negative x squared. Perfect. And we want to find f dash of x. So this f of x. Perfect. So let's write that. F dash of x is e negative x squared 2x minus 2 x to the power 3. Perfect. State the nature of the stationary points of the graph of f at the origin. Okay, very easy. There's a quicker way to do it, and the way is to find a double derivative. For example, let's find a double derivative of f of x. Okay, and we want to find it at the origin when x equals 0. If the number is positive, which is right over here, 2 is a positive number, it means a minimum occurs, a local minimum. If it's a negative, it's a local maximum. If it's 0, it's a stationary point of inflection. But here, it's a positive number, so it is a minimum value. So we can say local minimum. Hope you spelled the right minimum, something like that, yeah. Find the maximum value of the function f and the values for x for which the function occurs. So find the maximum value of f and the value. Okay, so we know f dash of x, so we just need to let this equal 0 and we need to solve for x. Now the easiest way is just go on my calculator and I'll just go on menu, calculus maximum. And for f of x, comma x, yeah. So our maximum points that occurs at x equals -1 and x equals 1. So we can say x -1, -1 and x equals 1. And what's f of -1? And what's f1? So at f -1 and at f1, they have the same y-intercept. So we can say that's e -1, e -1. So pretty much we found these are our x and the maximum value of f. So max value is 1 over e. Perfect. That's the answer. Done. Find the values of d. So d, all elements or real roots for which f of x plus d is always negative. Okay, so what we know is that d here is pretty much a translation up or down. So what I'm going to do is go on my actual calculator and just say f of x plus d. Okay, and we want to add a slider. So what can we see? Let's say d is 0. Okay, well, what can we see here? Well, if we really zoom in here, what we want, so what we really want over here is we want this function to be like below the x-axis for it to be negative. For that to happen, d is what's going to translate it down. So d must be some value. If we're going to translate this down, we want to translate it down to its local max. And so if we go to the minimum value, which is 0.15, or not actually this is nothing, but we know our local minimum value, local maximum, this local maximum here is 1 over e. Like it's this point, if I go over here, maximum. So this point over here, if we say d is negative 0.368, we pretty much translate this graph down. So it's negative, but we want it to always be negative. So we want d to be less than that value. For example, if I say, take this over here, let's copy this. Let's just copy this and put it over here and put negative that value. What can we see? It goes below the x-axis, and that's what we want. So if we want to find the values for which d is always negative, we can say that d pretty much must be less than -1/e. Make sure you put that negative because we are translating it down. This is where people will make a mistake by just saying it's 1/e. And yeah, perfect. So, and if we go less than that, perfect. It goes down forever and it will always be negative. Hope that's right. Perfect. Let's go to the next question. Okay, let's look at this. Find the equation of the tangent to the graph at x equals -1. Okay, so find the equation to the tangent at x equals -1. So for this one, what I'm going to do is just use my calculator. So I'll go over here and just say, I'll go menu, calculus, tangent line of f of x, comma x at -1. And that's e-1. So it's just y equals e to the power of -1. That's it. Find the area enclosed by the graph of f and the tangent to the graph of f at x equals -1, correct to 4 decimal places. So what we want to do is find the area enclosed by the graph of f and the tangent at x equals -1. Okay, so if we come back to this graph over here. So we just take these all here, and let's say d is 0, because like let's take d out. So, and yeah, so this over here is what our graph of f is. And the tangent at x equals now, which is just, we've already calculated that, which is what, e to the -1. Wow, I'm going to put this e to the -1. Okay, so it's this over here. Perfect. We want to find this area that's enclosed, which is over here. So to find that, I would say area must be from -1 to 1 of the upper function, which is e to the -1, minus your f of x dx, and that gives you what? So using your calculator, -1 to 1, e to the -1 minus f of x dx, and that gives you, control enter, this over here. So to 4 decimal places, that's 0.3568 units squared. I hope that's right. Let m and n be a point on the graph of f where m must be between 0 to 1. Find the minimum distance between m and the point this and the value of m for which this occurs. Okay. Alright, so what I'm going to do here is I'm going to use the distance formula here. So distance, well, in terms of m, so distance in terms of n is what? Well, this point over here is, let's try our n value. To get our n value, you just have to sub in m to the function of f. So what I'm going to do is, if we sub in, what's f of m? It's just m squared e negative m squared, and we're going to minus that by e, plus, and we also want to square it, sorry, plus, now it'll be m minus 0, which is 0 squared. Alright, have I done that right? So this minus e squared, yep, should be right. And I'm just now going to use this on my CAS and do this whole thing here. So I just said, what's f of m minus minus e. We're going to square that plus m squared. And that gives us this ugly function. So I would write this function because it's 3 marks. So it will be e negative m squared square root negative 2m squared em squared plus 1 plus m squared plus e squared times e 2m squared plus m to the power 4. Now we have this, and what's d dash of m? Let's find d dash of m. So let's go do that. In terms of m, this whole function, take this, push it in here, done. And it gives us, oh my god, gives us a big and ugly function. I wouldn't suggest doing it. I'm just going to say d dash of m equals 0. And we're going to solve for m. The fastest way I'm going to do this is go menu, calculus, and I'm going to find the minimum distance. So I'm going to press minimum and copy this whole distance formula here, push it in there, comma, wait, did I put it inside the function? No, I didn't. Ooh. I'm going to copy this, cut this, put it over here, comma, m, and we know m is from 0 to 1. And that gives us control enter. Aha, this is our m value. So our m value is to 3 decimal places is 0.783. So find a minimum distance at m and the value of m. So we have this and we say, what's d of 0.783? That's going to give us, so what's, our minimum distance is this one over here. Given that our m value is this, that gives us 2.511. Perfect. That's that. Hope that's right. Question 2. An amusement park is planning to build a zip line above a hill of its property. The hill is modeled by this from 0 to 30, where x is the horizontal distance in meters from the origin and y is the height in meters above the origin as shown. Find dy dx. Okay, so I'm going to just control n this and I'm going to define the new function. So, okay, f of x as 3x times x minus 30 and squared 2000. Alright, so dy dx is very easy. So what's that? It's just over here. So we can say dy dx 9 x minus 30 x minus 10 over 2000. Find a set of values for x for which the gradient of the hill is strictly decreasing. Here they're trying to trick you. I just saw this right now. We're talking about the gradient which is strictly decreasing. So what we want to find is, you know how the gradient's dy dx? To normally find when it's strictly decreasing, we always find the derivative of the thing that we want to find it to strictly decrease and be less than 0. So here, what we're going to do is we're going to double derive it because this is the gradient and they're telling us to find it when it's strictly decreasing. So we're going to say dgx of dy dx. So like the double derivative of this function where it's less than or equal to 0, where it's strictly increasing. We're going to calculate that. So I'm just going to go on this and just say, in terms of x, so double derivative of the function f of x, where it's less or equal to 0. And I'm going to solve that. Answer, comma, x. And gives us that x is less than 20. So we can say that x is an element from negative infinity to 20 inclusive. But here you must be careful because they did give us a domain where it must be from 0 to 30. So this over here, just make sure it's from 0 to 20. Hope that's right, yeah. So, because it's included, so it should be 0 to 20. Is it? Because we double derived it. Does that change it? I know the 20 is right, but what about the 0? Do we include it or not include it? Because we just found a double derivative of it. Not too. I think we do include it. Yeah, I have a look at this after. Yeah, it's only 1 mark anyway. It should be excellent number from 0 to 20. I'm not too sure. Should we? Do you include it in this term? I don't think you include it because when you derive, like when you normally derive a hybrid function, the derivative, like these values over here, they don't become included after, like when you derive them. So I'm just thinking, would that mean that, yeah, you don't include 0? So x an element from 0 to 20. I hope that's that. I need to double check it after, maybe. I need to check the answers after, because I haven't checked the answers. I just do these exams before having a look at the answers, so there may be some mistakes, but yeah, hope that's right. I'm gonna have to look at it, but yeah. The cable for the zip line is connected to a pole at the origin at a height of 10. So okay, perfect, which is over here. And is straight from 0 to A. So okay, so here this line is straight. Where 10 to 20, so from 10 to 20, this over here. So A is from 10 to 20, which makes sense. This straight section joins the curve at A on B. The cable is then exactly 3 meters vertically above the hill. So here, yeah, it's 30, where A is between to X to between to 30. Okay, as shown in the graph. State the rule in terms of X for the height of the cable in above the horizontal axis for X is 8 to 30. All right, so 8 to 30 is this over here. All right, perfect. So what I'm going to say here is, because we know the height here is just 3. This always is 3, as is shown by us. So it would be, again, this is the same function, but it's been translated up 3 units. So, well, we defined it as f of x. So we can just say what, on a calculator, what's f of x plus 3? And it's this over here. So let's call that p of x here. So p of x is 3x to the power 3 all over 2000 minus 9x squared all over 100 plus 27x all over 20 plus 3. Find the values of x for which the gradient of the cable, so the gradient of the cable, okay, is equal to the average gradient of the hill for 10 to 30. Okay, so let's look at it first. Okay, find the values of x for which the gradient of the cable. So gradient of the cable, well, we know the equation of the cable, and we can easily find the gradient, which is just what? P dash of x, which is what? So go on our calculator and just say, we want to find the gradient of this. Oops, why did I do that? Put it over here. Done. So our gradient is this, so we can say it's 9x squared over 2000 minus 9x over 50 plus 27 over 20. And it's equal to the average gradient. So the average, which is, to find the average, normally it's, gradient from x to 10 to 30. The average gradient of the hill, which is, we're saying that it's f30 minus f10 all over 20. So that'll be f30 minus f10, 20, which is negative 3 on 10. And we just equate those. So what's 9x squared, 2000 minus 9x over 50 plus 27, 20 must equal negative 3 on 10. And we want to solve this over here. Oops, yep, this over here. Let it equal this over here, comma x, which gives us these two values. Yeah, so find the values. So there's two values, perfect. So our values is x is negative 10 root 3 minus 6 all over 3, and x is 10 root 3 plus 6 all over root 3. Done. I'm just going to make this smaller. Perfect. Let's go to the next question. The gradients of the straight and the curved section of the cable approach the same value as x equals a. So there is a continuous and smooth joint at A, which makes sense, absolutely. So here, right over here, they join at A, and so continuous. Set the gradient of cable A in terms of A. Well, we already know the equation of P of x, so we know what's P dash of x. Isn't it just the gradient at A? So if we go on our calculator, we already calculated, so it's, if I'm not mistaken, yeah, so it's this here, given that x must equal A, x must equal A. And it's that. So yeah, so set the gradient of cable A in terms of this, it's this one. So we can say P dash of A, 9a squared over 200,000 minus 9a over 50 plus 27 over 20. Find the coordinates of A with each value correct to 2 decimal places. Okay. Well, if they are continuous at that point, their gradients must be the same at this point, which should be true. Because this one is continuous, that the gradient's the same, and we already know the gradient of this by using what we've just calculated. We just need to find the gradient of this from 0 to a. Okay, so what can we say? Well, okay, so let's just try to find the average gradient, like that. So from, it will be, okay, because they think in the same place. So what's P of A? What's P of, well, we've defined P, haven't we? No, we haven't. So, okay, take this over here, and we want to say when x is equal to a, what's that value? Which is this one over here. So I can say that minus 0, a minus, then what's it? So wait, that minus 10, because that's our b value. So I hope that's right. So we're saying that 3 a to the power 3 all over 2000 minus 9a squared over half 100 plus 27a over 20 plus 3 minus 10, and then we can say a minus 0, which is just a, all over a. So here this will give us our actual average gradient of this line. Because they are continuous, we already know the average value at this point, this gradient, from this. So we can equate this, we can equate this to this. Let's do that. So this should equal 9a squared over 2000 minus 9a over 50 plus 27 over 20. I hope that's right. The coordinates of a. Yeah, let's try that. So let's just write that. So we're saying this over here minus 10 all over a should equal this over here. Wait, should equal this over here actually. Well, should equal this. What have I done? Wait, have I just mistaken something? It's this one, yeah. So the gradient when it's equal to a, this. Perfect, and we want to solve answer, comma a. Okay, and a, they give us these values, but we know that a is between, go on top, a is between from 10 to 20, so it can only be a equals 11 point this. So we can say that a is 11.12, and yeah, so it's very easy to find the actual thing now, because now we know that we can just say this, given that x is equal to this value over here, it will give us our y coordinate, which is, we can say the coordinates of a is 11.12, 8.95. That's your coordinates of a. Yeah, so that's that. I hope that's right. Good. Find the value of the gradient at a, correct to one decimal place. Okay, very easy. It's just p dash of 11.12. So, oh my god, it's such a mess. This is not good. I haven't defined a lot of stuff, and yeah, this is not good to have on your CAS, because then you get confused, which is not good. Don't do this, what I've done here. So this over here, given that x must be this. And that gives you negative 0, so wait, negative 0.1. Yeah, that's that. So during a telephone call, A phone uses a dual frequency electrical signal to communicate with telephone exchange. The strength f of a simple dual tone frequency signal is given by this function, where t is the measure of time where t is greater than 0, part of the graph of y equals f of t is shown. Set the period of the function. Okay, so when does it repeat? Well, it repeats from here and here and here. So here is a full repeat. You see this one right over here? To find the period, normally it's just when do they repeat, and yeah. So this one over here is the same as this one over here. So what's that distance? That's going to give us our period. So the distance is 12. Your period is 12. State the values of t where f of t for the interval this. Okay, let me actually define this function, and let's go and control n this. Now what's f of t? Given the sine pi times t over 3 plus sine pi times t over 6. Okay, so find the values of this. So we want to find solve f on t, which equals 0 comma t, given from 0 t to 6. And that gives you these two values. So t equals 0 and t equals 4, t equals 6. Done. Find the maximum strength of the dual tone frequency signal. Okay, very easy. So what I'm going to do with my calculator, go menu, go on algebra and just go, oh, not algebra, calculus, maximum. And we want to find the maximum of f of t from, let's say, 0 to 6. Oh, what happened here? Oh, sorry. Given t, given. Okay, we get the t value, which is good. So what's f of this value? And that here is our maximum. So our max is 1.22 decimal places 1.76. Find the area between the graph of f and the horizontal axis for 0 to 20. So what we want from 0 to 6. So what we want is this area over here. So from 0 to 6. This area over here. These two. So that will be, your area will be from 0 to 4 f on t dt plus, actually minus, let's make it easy, minus 4 to 6 of f t dt. Perfect. Which should equal, alright, so let's do that. So we're saying from 0 to 4 f of t dt plus, actually minus 4 to 6 f of t dt, and that's 15 pi, 15 over pi, units squared. Let g be the function obtained by applying the transformation t to the function of f. Okay, so when we apply this transformation to the graph of g, no, to the graph of f, we obtain g. Okay, where a and b, c are real numbers, find the values of a and b and d, given that from 2 to 0 g t dt plus this has the same area calculated in part d. Okay, what can we do here? 2 marks. So this one looks tricky. 2 to 0. That's stupid. Here, just rewrite that as just what? Let's rewrite that as what? 2 to 6 g on t minus 0 to 2 g on t. It's not good to have, oh, I'm supposed to write d on t here too, but it's not good to have these, it's supposed to be the higher number minus the, because now that makes everything easier. Let me just rub this off a little bit. Okay. So g on t dt minus 0 to 2 g on t dt. What do we know? It has the same area as this, so when we calculated this area from 0 to 6, so from this point to this point, we calculated this area. Yes. And this one over here, what's it calculating? So 2 to 6, so because it has the same area, it should have the same kind of shape. So from 2 to, so we're saying from 2 to 6. So 2 to 6 probably has, yeah, so 2 to 6, and we can see that it's positive because of like it has no negative here, which so it should be like a big, probably has like, yeah, something like this, like a big 2 to 6 like that. And so 0 to 2 must be below the axis because it has that negative, and it's trying to make it positive because it's area. So it's 0 to 2. So like this. So what can we do? Okay, wait. Here, I see what the actual thing is telling us. Okay, so if I just draw this a little bit much, I can see something. If I do some transformations to... Wait. That should be the function obtained by transforming f of t to this. Okay. Applying the transformation of x. Okay. If we want to make sure to get the yellow graph to look the same as the orange graph. That's what we're trying to find. Yeah, that's what we're trying to get right now. So I'm just going to make this nicer. Okay, so it's going to look like that. Like that. Yeah, so to do that, what I think we will do is think of it like this. Well, the best transformation that I would think you should do is we'll first have to reflect it along the y-axis. So imagine like this yellow graph. So let's say that was here. This was 4 here. And this was 6 over here. So if we like reflected it, it will look like this. It will look like this if we reflected that yellow graph. And then if we translated it 6 units to the right, it then would look like the orange graph, which is the perfect, yes. So, okay, what have we done? Well, we first reflected it along the y-axis. So your b value here, should be -1. There wouldn't be any dilations. It's just a -1. It's only a reflection, because if there was a dilation, they wouldn't even have the same area. Something would have changed in the area. So it's just b equals -1. I hope that's right. And our a value is just the same. A equals 0. A equals 1. There's not any transformations that are done to a. So a should equal to 1. Perfect. What else? But we also know that we did transform. We haven't also, for the translations of d, like d is up or down. We haven't even translated up or down, by the way. So d must just equal 0. That's good. And for our c value, which is translating it right and left, we do translate it to the right. So to get this graph here, we do translate it to the right by 6 units to get it perfectly on top of the orange graph. So 6 units to the right. So your c value is 6. Is that right? So 6 units to the right. But the problem here is, I think they're trying to... Okay. We haven't taken in consideration that if we 6 units to the right, we can also... There's also the possibility of it going... We can translate it more, and we can get this over here. And more, like, you got to remember that when you're we're not... It's not like a function. It's always repeating. So I think this is where the... I don't know. Should we leave as this c equals 6? But that's only one of the solutions. It could have been translated to the right like many times. Like it could have just been like it could have been translated 18 units, and we could have got this over here. Wait, if I'm not mistaken, it should be something like we could have got this over here, or so this is where we need to be careful. So I think for us to determine that, the best way... Well, what's the period? Okay, so if we, let's say it was that, it would just be repeating every 12 units. So would that be C plus 12n? Where n is an element of all integers. Is that right? Positive integers. Be careful. We want positive integers, not negative. We don't want to turn to the left. Careful here. We don't want to translate it to the left. So we want positive integers. Is that right? Yeah. We must also include zeros. So union also zeros included, because, I mean, if you put 0, it's 6 units to the right. C is 6, which is the true. That's also a solution. All right. I don't know if that's right. I don't know. I actually don't know. This question is quite difficult because did they want it in that solution? Because it's repeating. That's what I'm kind of confused here. It repeats. Yeah. I hope people understand what I mean. Yeah. So because like the function is always repeating. So it could have not just went on to this graph, but it could have went like to, you know, this graph over here or this graph over here. So yeah. Look, I don't think it matters, to be honest. I think you just need maybe just C equals 6. It could be a solution. They should give you the mark, but I think, yeah, to be exact, it could, yeah, maybe this here for C. But the other ones are easy. B equals -1, A equals 1, D equals... I'm certain that those are right, but C, 6 plus 12n, where n is an element of all integers in the positive. Union, yeah, and 0 is included. I'll double check the answer for that one. The rectangle bounded by the line y equals k, where k is an element of all reals plus the horizontal axis, and the lines x equals 0 and 12, has the same area as the area between the graph of f and the horizontal axis for one period of the dual tone frequency. So we're saying that one period, so just let me rub this whole thing off here. So we're saying that one period, so from here to here, this area is pretty much equal. So where k is like y equals k, some value of y equals k, let's say it's over here. This is y equals k. The area of this, from, did it say from 0 to, from the line 0 to 12. So this line over here, this over here, this over here, this rectangle, sorry, this rectangle has the same area as that as the area of that. So that's not too bad. So what's the area of the rectangle? It's very easy. So the area of the rectangle is what? It's just 12k, because yeah, that here, the length here is 12, and k, so 12k equals from, what's the area of the actual graph? So from 0 to 4 of f of t, so f of t dt, minus 46 dt plus 6 to 8 minus dt minus 8 to 12 f of t dt. And yeah, so k should equal, let's do this in a calculator. So 12k equals this over here plus 6 to 8 f of t dt plus, actually minus 8 to 12 f of t dt. And we want to solve answer, comma, k. So k is 5 over 2 pi. 5 over 2 pi. That's that. Question 4. So let's get this done. It says that the Lawrence birdwing is the largest butterfly in town A. The probability density function that describes its lifespan x in weeks is given by this. Find the mean lifespan of the Lawrence birdwing butterfly. So it's just from 0 to 5. So the expected value of x is from, so it's pretty much x f of x dx. Let's do that on a calculator. Let's create a new document and say, let's define f of x. So f of x is 4 over 65 times 5x to the power of 3 minus x to the power of 4. Okay, that's that. Enter. So yeah, so we're saying from 0 to 5 x times f of x dx, which is 10 over 3. Done. In this sample of 20 Lawrence bird-wing butterflies, how many butterflies are expected to live longer than the 2 weeks? So we want to find the probability that, say, I expect it to live longer than 2 weeks. So x is greater than 2. So, and we find this, we also want to multiply by the 80, because how many butterflies we want to find. So, doing this in our calculator, so we want to find from 2 to 5 of f of x dx times 80. That gives us 73. 73 butterfly. Wait, butterflies? Butterfly, yeah. Butterfly. That's that. What is the probability that a Lawrence bird-wing butterfly lives for at least 4 years, given that it lives for at least 2 years? So, probability that it lives 4 years. So, 4 weeks, given that it lives for 2 weeks. So, x is greater or equal to 2. So that's the probability of x is greater than or equal to 4 all over probability of x is greater or equal to 2. Okay, that's easy. Let's do it on our calculator. So 4 to 5 of f of x dx and 2 to 5 f of x dx. That gives us, to 4 decimal places, 0.2878. Done. The wingspans of Lawrence bird-wing butterflies in town are normally distributed with a mean of this and a standard deviation of this. Find the probability that a randomly selected Lawrence bird-wing butterfly in town has a wingspan between this and that. Corrected for decimal. That's very easy. Just do on our calculator. Menu, probability, distributions. Because it's a normal, we're going to go normal CDF. Lower bound is 16. Upper bound is 18. And our mean is 14.1. And our standard deviation is 2.1. Okay, there we go. So to 4 decimal places, that will be 0.1512. Is that right? 0.412. Perfect. Okay. A Lawrence bird-wing butterfly is considered to be very small if the wingspan is in the smallest 5% of all the Lawrence bird-wing butterflies in town A. Find the greatest possible wingspan in centimeters for a very small bird-wing butterfly in town A, correct to 1 decimal place. So if I'm just going to draw a normal graph here. A Lawrence butterfly is very small if its wingspan is smaller. So let's say this value here, some value of x, and if it's smaller than here, this is 0.05 for Lawrence butterfly. Find the greatest possible wingspan in centimeters for a very small Lawrence bird-wing butterfly. Okay, we just need to find that value of x, which is very easy. Just go on menu, probability distributions, go on inverse normal. The area is 0.05. Your mean is 14.1. And your standard deviation is 2.1. Enter that, and that gives you here. Perfect. So it is 10 point to 1 decimal place, so it's 10.6. Alright. Does that look right? To 1 decimal place. Look good. Find the greatest wingspan center for a very small butterfly in town A. Okay, that's that. Each year, a detailed study is conducted on a random sample of 36 Lawrence bird-winged butterflies in Town A. A Lawrence bird-winged butterfly is considered to be very large if its wingspan is greater than this. The probability that the wingspan of any Lawrence bird-winged butterfly in Town A is greater than this is this. Correct to 4 different places. Find the probability that 3 or more of the butterflies in a random sample of 36 Lawrence bird-winged butterflies for Town A are very large. Okay, so this is binomial distribution now. So just go on menu, probability, distribution, go on binomial CDF, and the number of trials is 36. Your probability of success is 0.0527. Is that right? 0.0527. Your lower bound is, because it says the final probability of 3 or more, so 3 to 36. Enter, and it gives you over here 2 4 decimal places. This is 0.2947. The probability that n or more butterflies, so probability that x is greater or equal to n or more butterfly in a random sample of 36 Lawrence bird-winged butterflies from Town A are very large, is less than 0.01%. Find the smallest value of n. Find the smallest value of n. Look, this one, well, this one over here that we just calculated, because I'm quite lazy, I'm feeling quite lazy today. We already calculated that when probability of x is greater or equal to 3, we get this value over here. If we say, let's start doing a guessing check. Let's check when n equals 4, 5, 6, and let's say if it's less than 0.01. Because, yeah, that's the best way to do it. Because right now, I'm feeling dead. So if we go to probability distributions and go to, what are we trying to do here? Okay, we're doing binomial. Let's say binomial CDF. Number of tries, 36. Probability of success is 0.0527. Your lower bound here is, let's check, it's 4, and your upper bound is 36. So, okay, this number here is not less than 0.01. Let's check 5. Aha, 0.03. Nearly there. Let's check 6. Aha, 0.01. That is nearly there, but remember, we want it to be less than 0.01 here. It's still greater because it has this. So probably the next one is the right one. If I put 7 here, when n equals 7, 0. Okay, perfect. This one is less than 0.01. So n equals 7. Hope that is right. For a random sample of 36 Lawrence birdwings, a butterflies in Town A, P is a random variable that represents the portion of butterflies that are very large. Find the expected value and the standard deviation of P correct for decimal places. So the expected value of P naught, if you don't know, it's just your value of P, which is 0. This is all in your, by the way, formula sheet, these formulas, so 0.0527. And your standard deviation, so your SD for this value is just square root of P, which in this case was 0.0527. 1 minus your P value again, 0.0527, all over your N value, which is 36. That should equal to what? So what's the square root? So what's the square root of 0.0527? 1 minus 0.0527 over 36. It gives you, for decimal places, that's 0.037. 2. Is that right? Yeah, I think, yeah, 0.03272. What is the probability that are we nearly done? Okay, well, these probability questions are so boring. What is the probability that a sample proportion of butterflies that are very large lies within one standard deviation of 0.527? Correct to 4 decimal places. Do not use a normal approximation. Okay, if it's one standard deviation, think of it. We're saying what is the probability. So remember, your standard deviation, well, they're not telling us to use normal approximation, but this is what it looks like. If I was going to use a normal, but we're not going to actually use a normal, but let's say this is your standard deviation, and this is your SD here. This is your plus, and this is your minus. So here they're telling us, what is the probability that a sample proportion of butterfly that are very large lies within one standard deviation of this value? So we're saying this value minus your standard deviation, which is this, which is what? Like just what's 0.0527 minus, you know, this value over here, what we got. That will be 0. It will be 0.0, let's say 15, is less than p dash, less than, and because we minus that, we must add, because remember, this is what we just did, and we also want to add, because this value over here is this over here, and so we minus it, but we also want to add that value. So we just put it over here. On plussing it, it will give us 0.8, yeah, so it's 0.899 pretty much. So they gave us this, which is what? Well, just multiply these values by your n value to get the actual much nicer. To change, let's change this p dash to x. We know that, yeah, so you know that p dash is x over n. So let's calculate x from it. So this here, multiply it by 36, because we're dealing with still 36 of them. So this one over here will be 0.55, which is just 1. Must be less than x, must be less than, what's 0.08 times 36? And that will be 3. Okay, so that's easier to deal with. So now we can just use probability. So menu, probability, distributions, binary CDF. The number of trials is 36. Your probability of success is 0.0527. Your lower bound is 1, and your upper bound is 3. Enter that, and it gives you, to 4 decimal places, that's 0.73 80. Is that right? 0.73737. Yeah, I hope, yeah. What is the probability that a sample of butterflies that is very large within 1% deviation of this? So 1.3, so we know that there was 36. 0.0527. Yeah, I hope that's right. I need to double check the answers. The Lawrence birdwing butterfly also lives in town B. In a particular sample of Lawrence birdwing butterflies from town B, an approximate 95 confidence interval for the proportion of butterflies that are very large was calculated to be this. Correct to 4 decimal places. Determine the sample size using the calculation of this confidence interval. Very easy and nice. So we know that 0.0234, this one over here, must equal to your actual what? It would be equal to your P minus your Z, which is for 95, it's 1.96. The square root of P, 1 minus P over N. And for the other one, 0.0866, it's the same, but there's a plus over N. So we have two simultaneous equations that we can find P and N, but we just want N. So let's use our calculator here. Go on menu, algebra, solve system equation for the values of P and N. Okay, so we want 0.0234. Yep, 0.0234 equals P minus 1.96 times P 1 minus P. Oh, actually just, so P 1 minus P over N. Okay, I'm going to copy this, paste over here, and I'm going to put a plus here, and I'm going to change this over here to 0.0866. N is therefore 200. Done. Question 5. if f of x is this, the tangent to the graph of f at a, which is this one over here, where a is between 0 to 1, intersects the graph of f at point P over here, intersects the horizontal axis at Q. The shaded regions shown in the diagram below are bounded by the graph of f. Its tangent at x equals a and the horizontal axis. Find the equation of the tangent. So find the equation of the tangent of graph f at x equals a in terms of a. Okay, let's make a new document. I just want to get this exam done now. So tired. Wow. F of x is 1 minus x to the power of 3. Okay, so we want to find the tangent. So just menu, calculus, tangent line of f of x, comma x at a. And that'll give us this. So your y equals 3a squared x plus 2a to the power of 3 plus 1. Find the x coordinates of q in terms of a. Okay, so just say solve. This equation over here equals 0, comma x. Done. So your x coordinate is x 2a to the power of 3 plus 1 all over 3a squared. That's done. Find the x coordinates of P in terms of A. So P is the intersection of the graph this and the graph of f of x. So we can just say f of x is equal to negative 3a squared x plus 2a power 3 plus 1. So we want to solve f of x equals this over here, comma x, done. So x, your P coordinate is just x equals negative 2a. Done. Alright, that's the last page. Wow, okay. So let a be the function that determines the total area of the shaded region. Find the rule of a. So in terms of a, so it's going to be a on a. Alright, so we can say from this point P, which is what? P is negative 2a. So this point is negative 2a. So from negative 2a to a, so from negative 2a to a, where the upper function is the line negative 3a squared, which is negative 3a squared x plus 2a to the power of 3 plus 1 minus f of x dx. And from here to this point over here, so from a to 1, the graph, yeah, so it has the same thing. So from the graph from the upper function, still the line minus f of x. So again, negative 3a squared x plus 2a power 3 plus 1 minus f of x dx plus from 1 to q, which q is what? The x coordinate of q is this. So from 1 to 2a to the power of 3 plus 1 all over 3a squared of the function negative 3a squared x plus 2a power 3 plus 1 dx. And that should give us our a on a, our rule. Wow, that's a lot. Just let me make this smaller. Oops. Alright, make this smaller. Bring this over here. Perfect. So this would give us this. So let's write this in our CAS. It's a lot, but yeah, that's the problem. So negative 2a to a. I'm going to just copy this function over here. Minus f of x dx plus a to 1, this function minus f of x dx plus 1 to this here, this dx, and time we get this over here. So that is your actual rule. Let's write that. A power 6 plus 8a power 3 minus a squared plus 2 all over 12a squared. Done. Find the value of a for which the a is minimum. Okay, so let's just a on a must equal 0. So for a to be minimum, I'm just going to do the easiest way. Go on menu, go on calculus, go to function minimum of this function over here, comma a, comma, what is the domain of a? Like, what can a be between? Well, here it says that a can be between from 0 to 1. Enter. Aha, this is our value for a. The value of a for which is a minimum is what? 10 to the power of 2 over 3 all over 10. That's it. Consider the regions bounded by the graph of f inverse and the tangent to the graph of f inverse at x equals b, where 0 to less than b less than 1 and the vertical axis. So find the value of b for which the total area of the region is minimum. I'm so confused. Wait, consider regions bounded by the graphs of f inverse, the tangent to the graph of f at x equals b, where b must be from 0 to 1, and the vertical axis. So what I'm going to do here is I'm just going to draw it, because it's too much words and stuff. I'm not fully comprehending what the hell they're saying. So what I'm going to do is, I'm going to actually first solve for the inverse to get the inverse equation. So I'm just going to say solve f of y equals x, comma y. So this is our inverse equation. So I'm going to copy that, and I'm going to go on graph. And we're saying, let's draw this, put it here. Let's draw this here. And let's draw an equation to the tangent at x equals. So if I go on menu, not this, so menu, calculus, tangent line of this over here, comma x at the value of b, we get this equation. And copy that, and let's put it here, and enter, and let's put a slider. And we know the slider must be from 0 to 1. So put a 1 here, we must put 0 here. Perfect. So this is what our, oops, it's too ugly, so let me just move these away. Okay, so here is our, let me just zoom it in. Zoom in, okay. Perfect. Perfect. So, well, what can we see? Well, from 0 to 1, we can always see that there is 2 areas over here. Yeah, so there's 2 areas over here and over here. So what can we say? Well, let's find, and we can always see that the line is always the upper function. So that's good to know, actually. We just need to actually just find a point of intersections. For example, if let's say this value was b, blah, 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 the point of intersection from, let's say from 0 to this point, which is b, and we also find the point of intersection from here, we can actually just find this area and this area. And that then, find the minimum value of that area. So what I'm going to do is, I will go on, control this, and create a new problem. And what I'm going to do is I will say, add calculator. So what I'm going to do, because I don't want to mix a lot of stuff up, so find the value for which area of the region is minimum. So because I know that this equation, we can find the points of intersection. Let's say this over here equals this over here. And we can enter that, and we can solve, answer, comma, the value of x. So here is our point of intersection at this value and this value. So that's good to know. So let's now go into this graph and say, let's find the area from, from 0, so from 0 to b of the line, which is an ugly function. I don't want to write that, but I think we do have to. So negative x over 3b minus 1, 2 over 3, minus 2b plus 3. Yeah, so minus x. Minus 2b plus 3. Yep, so this minus f inverse of x. dx plus from b to, what was the other one? It was negative 8 b minus 9. And the same equation. So this whole equation over here, just copy it. Copy, paste. That. Okay. I'm going to take this and I'm going to make it so small. I'm just going to put it over here. And so, doing that, let's write that on a calculator from 0 to b of this function minus this over here. Oops. So wait, minus your inverse, yep, dx plus from b to this value here. Let's recopy this whole thing. Wait, what am I? Oh my god, did I mix every... Okay, I'm just going to delete the whole thing. I just did so much problems. Okay, let's rewrite it. So 0 to b. So from 0 to b, this function over here minus this one over here. Why is it? Okay, cut this over here. Dx plus b, this point. And I want to copy this, Control C, and paste it back here, dx, enter. Okay, now it's good. So we get this, and so this is our actual area, and we want to find out where it's at minimum. So if I just go menu, calculus, minimum value of this whole thing, comma b, where b is between 0 to 1, this is our minimum value, 9 over 10, done. Wow, b equals 9 on 10. Find the value of the acute angle, find the value of the acute angle between the tangent to the graph of f and the tangent to the graph of f inverse at x equals 1. Okay, so if we go over original, okay, so I'm just going to rub this one out then. Okay, so this is f inverse, and if I draw f of x, if I sketch f of x here, and this is f of x over here. If I can find for both the tangents at x equals 1 for both of them, for example, if I go to menu, calculus, tangent line for f of x first, x at negative, at what? At 1 actually, we get this one over here. So I'm going to take that, I'm going to put it over here. That's one tangent. The next tangent occurs for the inverse, which is this one over here. Enter, which at x equals 1. Okay. Okay, so that means that x equals 1 is what? So if you go menu, entry relation, x equals 1, so it's this. And I'm now going to rub these ones off. So I can really see between the tangents and the acute angles. So this is what we want to find. Okay, if we zoom in here, okay, done. So right over here, we want to find the acute angle. So if I'm not mistaken, if the acute angle would be less than 90, so it would be this one or this one. The way we would check it, the way I would actually check it, yeah, so the way I would check it is, wait, find the value of AQ between the tangent to the graph of f and the tangent to the ground of this. So let's just draw on our paper. Let's just draw on our paper here. Because here they're not asking us like in decimal places, so they probably need it in exact form. So if I draw this right here, and let's say this is here, this line over here is, x equals 1. And pretty much this here over here is that over here. So the tangent, so to find that angle, what I'm going to do is, well, we know that tan of an angle, let's say x, is equal to your gradient, which here is -3. So we can calculate x equals tan inverse of -3. Now I just want to calculate tan inverse of -3 to see how the angle would look. So if I go on tan -3 and say that this times 180 over pi, so that's -7. Okay, so it's actually giving us this angle over here. It's giving us this angle, that x angle over here. So find the value of that, but we want, okay, the acute angle. So if I'm gonna be honest, if I make this positive, if I say tan of 3, so tan of 3, we should get this now. Like we should get the positive x, not this negative. So yeah, and it should be, let's double check it. So if I come here and I put a plus here, yeah, so it's 71. So it's the same thing, yeah. And all we need to do pretty much is to find the acute angle. We want to find this angle over here, if I'm not mistaken. This is the angle that we want to find. This is going to give us our acute angle. So the way that I would do this is, because I know this over here is 90 degrees. If I can say pi over 2 plus tan of inverse of 3, now we're actually over here, it means. This is where we're here. So, because we know this here is pi, we just have to now say, because now we actually got this whole angle. Now we just need to say, what's pi minus pi over 2 plus tan of 3. So that'll be pi minus pi over 2, which is just pi on 2, minus tan inverse of 3. Is that it? That should be the answer. I want to double check it. Go on my calculator and just say, what is pi over 2 minus tan on 3? This over here. Yep, which is this, and if I say this times this 18.43, yes, that's an acute angle. It's less than 90. So yeah, that's that. So I think we can justify, so I'm going to make this little, our angle, so let's say theta is, well, it's, yeah, like our angle is pretty much this. Alright guys, that's that. I hope you guys enjoyed this video. Please make sure to like and subscribe to this channel. Yeah, this exam was not bad. Had some couple of good questions and a couple of boring and quite hard, I would say. But yeah, I hope you guys enjoyed this video and learned something. If you guys want more of these videos, please make sure to, support this channel by liking and subscribing. And yeah, I hope you guys have a good day and take care of yourself. Bye-bye.